Welcome! In this session, we will present a solution for the course project. So we are here in R, and as a core project, you have to predict the defaulters based on a neural network of two hidden layers with two neurons in each one of them. You have to use the parameter hidden equals to c, you open parentheses 2, 2, with which you will be indicating to R the number of neurons in each of the layers. So let's create our model. We're going to call our model model tree, which equals to the function neural net, we open parentheses, and as a parameter we're going to write the formula. Defaulter flag at 126, the sign that function likes an equal. Then we're going to put a point or a period to set to R that we are going to use all the variables less than defaulter type, which is the other dependent variable that we are not going to use. We are going to use the data training to train our model, and then we are going to use the parameter hidden equals to c2, 2 to indicate that we want two layers, and in the first one we want two neurons, and in the second one we want two neurons. If we had, for example, I'm going to write if I wanted a neuron or a neural network with, for example, two hidden layers with 5 neurons in the first layer and 7 layers in the second, 7 neurons in the second layer, then I would write c open parentheses 5, 7. But as I want a neural network with two hidden layers with 2 neurons in the first one, I write 2, and with 2 neurons in the second one, I write 2. So that's how I indicate R that I want two neural networks with two hidden layers with 2 neurons in each of them. Then as a raw fact, I'm going to write SSE, which stands to the sum of square errors, and I'm going to indicate that I want a threshold of the error of 0.05, and this works as a stopping criteria. Then I'm going to tell R that I want a linear output, so it doesn't have to smooth the solution. So I'm going to write true. Then I'm going to press enter and wait several minutes. And after about 30 minutes, we receive a warning message that says that the algorithm did not converge in one repetitions within the step maps. So we are going to try to simplify this model. We are going to erase one of the variables that was highly correlated. Do you remember that branch and region were strongly correlated? And we said that in one region there were several branches. So probably we could remove the variable region. And in addition to removing this variable, we are going to increase the threshold of the error. So we are going to help the model in order to convert. So we are going to remove defaulter type and also remove region. We are keeping branch. And we are going to increase the threshold error. I'm not going to write this on the console, I'm just going to run it from the script. So now let's wait several minutes in order to see that if this model converges. And finally, after several minutes, it looks that the model or the algorithm has converged, as we did not receive a warning message. So we have a model tree that we can observe here at the global environment, global tree, large neural networks. And now let's extract the result matrix from model tree. Model tree, the sign of dollar, result matrix. So we can see here the coefficients of the two hidden layers, the hidden layer 1, the hidden layer 2. And now let's plot the model. Plot model tree. and we can see here the model. We can see the independent variables, the layer 1 with the 2 neurons, and the layer 2 with the 2 neurons, and these were the independent variables, and we can see here the dependent variables defaulter flag. So once that we have plotted the model, let's predict the default probability. We're going to create the variable prediction3 equals to compute, the function compute of the package neural net, and as the first of the parameters will be the name of the model that we just created, the model 3, and the second parameter will be the name of the data set, which is testing. I press enter, we created the variable, and now let's create the default vector with the real data. We are going to create, we have already done this. I'm just going to run these 2 lines of command. In the first one, I'm creating the variable testing.original from the dataset credit cards, and I'm asking just for those observations that were not included in the partition. So I'm writing less partition, comma nothing. Get me all the rows that were not included in the vector partition and all the columns. And then I'm extracting from this testing original the variable defaulter flag. I'm extracting the dependent variable, which I'm calling real defaulter. I run these 2 lines of commands. And now let's extract the normalized prediction vector. So from prediction3 that we created here, we're going to extract the normalized prediction vector. So we just run this line of command, prediction.defaulter.norm3 equals to prediction3, the default probability that we computed here, and I'm just asking for the net result. So we have it over there, and now let's denormalize this data. Before denormalizing, we can look at it. Pred.defaulter norm3, and as you will see, it is already I would say normalized or a denormalized data. Just we have to remember this is between 0 and 1, so this was already denormalized as our dependent variable is between 0 and 1. So we don't have to do this in this specific case. We are doing this just to just for you, that you remember that you have to do this in the general case. So we are multiplying this prediction defaulter dot normalized 3 by the difference of the range of the real defaulter, and then we are adding the minimum of the real defaulter. Where does this formula comes from? This is the formula for the normalization. So we run this, and we have denormalized the data. And now let's create the classification vector. We are going to create a vector of 1. So we are repeating 1 5,781 times. That's the size of the testing data set. So we are creating a vector of 1. We can see this classification model vector, and we will see just a vector of, sorry, I didn't use the view with capital letter, classification model 3. And we have there a vector of 1s. Now let's add the zeros to that vector of 1. We are going to ask for those for this vector of 1s and for the prediction defaulter 3, the numbers that have a probability less than 0.5, please assign a 0. So that's what I'm doing here. And now let's look at the same variable. Let's look at the same variable, view classification model 3, and now you can see some zeros in this variable. You have some 1s and some zeros. And now let's convert this as a factor, because when we compute the confusion matrix, we have to compare factor with factors. And now let's finally create the confusion matrix. So we are using the function confusion matrix. The first parameter will be the classification model 3, will be the classification that we have already done. And then we are going to compare it with the real data from the dependent variable of the testing data set. So you can see it as dog factor. We are converting it as a factor to compare factor with factor. And then the third parameter, we are saying positive equal 1, and with this we are telling our those values that have a 1 are the positives. We run this and we have computed the confusion matrix. And let's look at the accuracy of the model. We have an accuracy of 0.7302. I think this accuracy is lower than the one that we obtained with the model of just one hidden layer. We have a sensitivity of 0.9 and a specificity of 0.30. Let's look at the confusion matrix that we obtained for the model 1. Let me see over here. I think we obtained in that an accuracy of 0.7336. That means that this model, even when we have two hidden layers, it isn't better than the one that we obtained with just one layer. With this, we are finishing this session. Thanks for watching.